Okay, now I would like to prove to prove the remainder of the proof of the second geometric form of Banach theorem. And you are at this page. You see that you have for all x like this, you have f minus 1, and it's because f is linear. This one is where f of x minus 1. You have this kind of form. And I say that B10 is a unit ball, which is symmetric. If this one is true for all z in B10, then that is also true for when you say minus z, because if z is the ball, minus z is also the ball, because this one is symmetric. So this one, this duration, it can be write like this. When I put, instead of writing z, I write minus z in this form. And if you take the supplement of this, the both sides have this relation, this kind of forms. And from here, you have this one. From here, because I can by 1 and 2 minus 2, when you put it, you have this, exactly this form. And you can say that this one, this map, this hyperplane separate three streets that were f for less than f for y, like this, and not epsilon. You have this kind of form. You have this one, where here the epsilon is 2r over 2 the log of x. That means that this hyperplane separates strictly the two convex subsets E and B. Okay, I will give you to finish this part of course. I will give you just a corollary, which is very, very important to this kind of corollary. This corollary says that this one states that when you have I take a corollary, we suppose that E is also a vector space. I take F, which is a linear subspace, is a linear sub of E, this kind of force. And then if you have this one, it's got the closure of F is not equal to E. That means that it's not equal to E. That means that F is not dense in E. It's not dense in E. Then there exists which is not equal to 0, which is in a dual E is star, such that you have this one. F of x might be equal to 0 for all x in F. This one is very, very important. So this kind of property we say here is exactly equivalent, the equivalent form. That means that when you have F which is dense in E, that means that for all F which a linear map of E, such that if for F is equal to 0 for all x in F, then F is necessarily equal to 0. If the function for all F, which is function, is equal to 0 in F, then it's exactly the same form. It's equivalent at this form. So if you want to prove that F is dense in E, you just prove that for all linear map, which is not equal to 0 in if is also equal to 0 on if F equal to 0 in E. The same. I'll give you the proof of this one. Very simple proof. Let's follow me. You can use just the second geometry form of Banach to prove it. Like this. If you suppose that F this one is not equal to E, that means that there exists x0 which is in E, such that this x0 is not in F. So we just consider this one, x0 and F, and this one, is not equal to this one. Just consider this one, and this one is closed, and this one is not closed necessarily. It's closed, but it's compact. This one is compact. This one is closed. So we are in the condition to prove to use the second geometric form, some form of Banach theorem. This one is closed. This is compact. This one is closed. Then there is this. There is this a map which is not necessarily equal to 0. Such that you have a map. So that means that there exists a plan like this of equation like this, such that you have f of x less than alpha, this one less than f of x0. X0. This one is a compact one, this one is a set of the of this kind. For all x in f, and here x0 is that the result will fit this kind of form. And you prove easy, you can prove easy that if you have this condition, that means that necessarily f of x is this one is equal to 0 for all x in f. It is necessary. If for any linear form which is bounded in a linear vector space, it is necessarily equal to 0. If you want, I can give you the proof of this one. It's simple to prove. Any linear map which is bounded on a linear vector space is necessarily equal to 0. What I'm going to show you. And if we say that this one is bounded like this for all x in f, we say that f here is a sub-vector space. So this one is true. That means that for all lambda which is positive like this, you have also f for lambda x is like this. For all lambda which is not negative for this, because this one is x. For all f is also in f. Is s in f, lambda f is also in f. It is true too. From here, that means that you have f of x less than alpha lambda. Then each lambda, when you take lambda to infinity, then you have f of x must be less than 0. What the frequent form is less than. In the same when you suppose that you took lambda which is negative, and this is 1, you have also f of x minus greater than alpha lambda. And you do the same thing. Lambda tends to infinity, you have f of x must be equal greater than 0. Less than 0, less or equal than 0 and greater than 0, then you have the f of x is equal to 0. Then we have linear map, which is any linear map which is bounded in the linear vector space is necessarily equals to 0. That's one of the equality of this kind of geometric form. Very many properties you can prove using this kind of. Now I will start. I will give you just the theorem of the Banach house, and maybe we finish tomorrow. For that. Banach house. Stenhouse theorem. Yeah. Here you are linear map, very simple too. The theorem says that when so you have linear family of operators like this. Family of operators. Of linear operators. Family of linear operators. Such that it's bounded like this. The norm of ti x of x like this one, for this one I is bounded. Is bounded. Then the supplement, or let's say for all EE, the norm of this one is also bounded. This one is also bounded. And here, that means that the resist M such that the norm of x must be less than M, the non-Prof. So just this condition. So yes.